So the start of week 5 is going to have us looking more closely at some of the data that we need to calculate in chapter 3. In doing this, I want to review a couple problems that we had assigned in week 3. One of them was problem 2.2 on page 607 of your textbook. You were to submit all your answers as a document or an Excel spreadsheet file via email. This is what the assignment was. We were to compute the data of heating degree days associated with the following weather data. So this is what they gave us. This is all they gave us. And we were supposed to then calculate how many heating degree days there were on that particular day. Most of you already sent in the spreadsheet, but this is what it looked like. So we can see that this information is what was provided for us in the outline of the question. What we had to do then was to create a spreadsheet. And this is an example used by one of your students. I just popped it in here. He did a nice job with it. So we can see from midnight to 4 in the morning, the temperature was 20 degrees, and that was a 4-hour period. So what we have to do here in this block is we've got to subtract the actual temperature from the 65-degree target temperature we want to heat the building to. And so to do that, if we click in the cell, we'll notice that the formula is listed here. 65 minus the value that's in B6, right? Here's B6 right here. Good. Now once we did that, we were able to do the same thing for each of the hours listed. We had to do the math. We could do it in our heads. That was probably the easiest way. 7 a.m. minus 4 a.m. is 3 hours. 10 a.m. minus 7 a.m. is 3 hours. Noon minus 10 a.m. is 2 hours. 5 p.m. minus 12 noon is 5 hours. There are other ways to do that. You could put the hours in here in military time, starting at 00 and going all the way up to 2400. But this is the way this was done. I bring this up because one of the students, when they submitted their work, these numbers, they didn't do this part here, right? Where I used the auto sum, where I added everything together in this row. I knew that that would be a great check. If there were more than 24 hours in the day, then I'll know that I did some math in here incorrect. And so one of you guys did that. And now once we've got that, we're able to just pull down and get this information to fill. Again, subtracting our number of hours from the 65 degrees Fahrenheit, and that you can see that that occurred in every single cell. All right. Again, the way that we did that is we could just click right, a double click there pulls it down. Now, the number of heating degree hours then, that math is going to be, we've got to multiply the item in D6, right? The number of degrees between, it's what we would call the delta T, between 65 and actual temperature. We need to multiply that times the number of hours that we need to make up that heat. We did that here, C6 times D6. And again, we can just carry that down. Yes, now the last cell that I have right here, I just goofed it up here. Let me Control Z that out of there. You'll notice that when I got down here, again, I did an auto sum. So this tells me the number of heating degree hours, which we divide by 24 hours. We can see that answer here is going to be C13, right? I'm sorry, E13, with 1,028 hours divided by C13, the number of hours in a day, 24, and that's the answer. So we had to construct this. Yours may not have looked exactly like this. Functionality was what's important. Another problem that I didn't assign, but I want to discuss, is 2-6. 2-6 is an interesting one. We have an outlying building that has a 25 kilowatt company-owned transformer that's connected all the time. A call to the local electrical contractor indicates that the core losses from the comparable transformers are nearly 3% of the rated capacity. So 3% of the 25 kilowatts, I'm going to highlight both those numbers because we're going to need those numbers. So 3% of the rated capacity is what will be wasted when the transformer is just sitting there, not doing any work. All right, now they give us our cost of electricity, 10 cents per kilowatt hour. That's numbers we'll need in our spreadsheet. They tell us that our demand is $10 per kilowatt, right? $10 per kilowatt. We'll highlight that. And then here's the kicker right here. The average building use is 10 hours per month. Again, we'll highlight that. Oop, didn't like that. Didn't like something I did there. We'll highlight that. And then they give us a clue that each month has 72 hours. And we want to know, this is the actual question, estimate the annual cost savings. I'm going to highlight that and make it bold. Right there. Because that is what we're supposed to do. Oh, that's not what I wanted. Oh, I did a bookmark. Never mind. Can't do that. So that's the stuff we're supposed to do here. We need to estimate the annual savings by putting a switch in so that the transformer only turns on when the building is used. All right, so let's go back to the spreadsheet. We can see that I actually made that here. All right. Oh boy, let me make this bigger so you can read it. 50%. Sure. So I repeated the verbiage right here. And again, I'm going to highlight exactly the important part here and estimate the annual cost saving. That's Control B. All right, that's what we're supposed to do. So from the data that we had, I made a spreadsheet. I knew I was going to use the transformer power use, or its rated capacity, 25 kilowatts. The core losses, 3%. Could have done that in just as a 3, but when I used the calculations on it, I would have had to use that cell divided by 100. Two ways of doing it. Either way are fine. The cost of energy, we said, was 10 cents a kilowatt hour. The cost of the demand was $10 per kilowatt. The building is being used for 10 hours a month. There are 720 hours in a month and 12 months in a year. So in order to calculate the energy savings, how much energy are we going to save? We got to remember that the switch is going to shut this thing off for 710 hours. So that's the clue, is that we determine how many hours we're going to save. All right, so here's the savings. And how did I do that? Well, notice I took B3, right? So B3 is the 25 kilowatts, and I figured out what that core loss would be. So B3 times C3 comes up to be 750 watts. 750 watts just sitting there, not doing any work, but making me pay for electricity. That's what we're trying to get away from. So, so that is the number of watts, and I have to multiply that times, notice G3 is the number of hours in a month, and we're going to subtract F3, the number of hours we use it, from it. So 720 minus 10 is 710, and we're going to multiply all of that times 12 months a year. That is going to give us our value. And that's going to say how much energy am I using during the 710 hours that the building is not occupied. All right, so that's what we have there. So that's the energy savings in kilowatt hours. Notice the demand savings is pretty small, okay? So the demand, it's only 750 watts. If a company has this huge, if it has a building that is only used a few hours of the day, they probably have electrical bills that are very, very high for other facilities that they're paying for. So this 750 watts, we really don't need to calculate that into the demand savings. It's going to be fractional. So last thing we have to do then is multiply the energy savings times the rate for electric use, which we have here. And there we go. And so that, of course, tells me that I'm going to use I3, which is right here, the number of hours used times D3 right here, which is the cost of electricity. So $639 is the correct